Thanks for clicking. Welcome to another Knowledge Math production. Today we're going to be talking about ratios and similarity between shapes like triangles from geometry class. Okay, how do ratios relate to this concept of similarity, or similarity relate to this concept of ratios? Okay, or proportions. All right, so let's get started here. So again, ratios. A and B are two quantities measured in the same units. The ratio is A to B, or A over B. A ratio is a fraction. The denominator can't be zero. Ratios are expressed in simplest form. Okay, ratios are fractions. We know that. What is similarity? So take a look. Basically, you're talking about the same shape, but one is a larger size than the other. So these two triangles, they're similar, right? They're the same triangle, but one is a larger shape. One is larger than the other, okay? These are not similar, okay? They're two totally different animals, so they're not similar to each other. But these butterflies they are similar because one's a smaller butterfly and one's a larger butterfly. And then these two shapes, they're not similar either. This is an octagon, right? 8 sides. And this is a trapezoid, it looks like, potentially. So they're not similar. They're not even the same shape. Okay, so that is similarity. All right, hopefully you remember that from shapes class at some point. So similar figures are figures that have the same shape, but not necessarily the same size. Okay, similar figures are enlargements or reductions with no irregular distortions, which means that you basically take the one shape and either blow it up, make it bigger, or make it smaller, okay? But you can't change anything else about it other than make it size bigger or make it size smaller, all right? Two figures are similar if one can be enlarged or reduced so that it's congruent, meaning exactly the same to the original. So if you take an original figure, blow it up, make it bigger, you can shrink it back down to the size it was originally, so then those two shapes would be similar to one another, all right? That's all it means to be similar. Okay, so here are two similar triangles. We're going to determine this missing side. So to determine the missing side, what we can do is we can set up a ratio over here on our first triangle. Now, there are a bunch of ratios that you can set up, and it doesn't matter which ratio you set up on this triangle, as long as you are consistent with your ratio on this triangle and that triangle. So here's what I mean. So I'm going to take the 4.5 and I'm going to take the 6 and write a ratio. So 4.5 over 6, that's my ratio. So now, if I line up the same two sides on this triangle, then I would line up x over 4, right? 4.5 is in the same location as x, and 6 is in the same location as 4 on the other triangle. These are similar. Since the triangles are similar, then these ratios have to be equal to one another. So 4.5 over 6 has to equal x over 4. And now we're going to solve this for x. So we can cross multiply. We're going to do 4.5 times 4. 5 times 4 is 20, 2 to carry. We owe 1 decimal. And then 4 times 4 is 16, and 2 is 18. We owe 1 decimal place, so it's 18. Equals 6x. Divide both sides by 6, and x equals 3. Okay, that's my answer. Now, what I'm saying to you is it doesn't matter which ratio you use. However, you want to be strategic about it. You want to use a ratio on this triangle that's going to involve the x on the other triangle, right? So the 4.5 you have to put in your ratio. You also could have used 4.5 over 7.5, but that would be the same as x over 5. Or you could have done 6 over 4.5. You could have done them upside down. That's okay, as long as you make the other ratio upside down, 4 over x. All right, as long as they line up, you're okay. Okay, in the figure, the two triangles are similar. What is the length of C? So C is the missing side. Now, we got to be a little bit careful here because these triangles have been rotated a little bit, right? Not all the stuff is in the same place. So let's redraw our PQR triangle so that everything's in the same place. Okay, so I'm going to redraw it so that it looks like the ABC triangle. Now the P has to match up with A because there's one mark there. And then Q has to match up with C because there's two marks there, so R must be over there. All right, now let's label our sides. P to Q is 4, and then P to R is 5, and then R to Q is D. All right, so now we got to be strategic about our choices. We only want to find the length C. That's this length. Okay, so we definitely want to put C in our ratio. So let's put C on the bottom. That way it'll be in the ratio. And then we also need another side on the triangle to use. Now, I don't want to use the 6. And here's why I don't want to use the 6. I'll try it. But if I use the 6, then over here on this triangle, I have to start with D. And now I have two unknowns, two variables in the same equation. And I can't solve it. So that 6 is not going to work. So I can't do that. So let me go back to, no, I don't want to use the 6. Let's go back to the over C again. And then I'm going to use the 10 side because the 10 lines up with 5. That allows me to put 5 up on the other one. And then C matches up with 4. So now I have only one variable, C, and I can solve it. 4 times 10, that's 40. 5 times C is 5C. Divide both sides by 5. C is 8. And there's your answer. Okay, so sometimes you got to be strategic about your choice. Sometimes you also have to be willing to redraw what you have because maybe it doesn't line up exactly the same way. Okay, so again, you can use similar triangles and proportions to find lengths that you can't measure directly in the real world. It's indirect measurement. If two objects form right angles with the ground, you can apply indirect measurement using their shadows. All right, so let's see what that looks like. So here's a 6-foot student. We're going to draw a picture. Here's a 6-foot student. They cast a shadow that's 17 feet. Okay, so my shadow would be on the ground, right? All right, I'm going to try to draw somebody's shadow here. I don't think it's going to work. All right, that's not too bad. There's their shadow. Their shadow is 17 feet. Okay. Now, a flagpole sitting over here. Here's the flag. Okay, flagpole. Casts a shadow that's 51 feet long. All right, so down here. Ooh. Oops. Hang on, let me erase this. I don't like where I made that line. I want to make my line here. So this whole distance here, all the way across, is 51 feet. Find the height of the flagpole. Oh, and this guy is 6 feet tall. Okay. I want to figure out how tall this flagpole is. All right, so what I'm going to do is I'm going to connect all this stuff. And hopefully you see that I make 2 right triangles. Let's show them to you. That's one there in purple. So I'm going to draw it up here. This side is 6. This side is 17. And this third side, I don't know. And then there's another one here. I'll put it in blue. The big triangle. Hopefully you see it. There it is. On that big triangle, we have H and 51. Okay, these are 2 similar triangles. So we can use the similar triangles to find how tall the flagpole is, H. So our first ratio will do 6 over 17. And the other one will be H over 51. 6 lines up with the H. 17 lines up with 51. Okay, now we're going to cross multiply. 51 times 6. 6 times 1 is 6. 6 times 5 is 30. So we have 306 equals 17H. Divide both sides by 17 to get H alone. We got to do it by hand. Into 306. 17 goes into 30 one time. 136. 17 into 136 is 8. 8 times 7 is, yeah, 8 times 7 is 56. 17 times 8. 8 times 7 is 56. 5 to carry. 8 and 5, 13. 136. No remainder. So H is 18 feet. So the flagpole is 18 feet tall or 18 feet high. And that's my answer. Okay? So that's what we're doing. We're using these similar triangles. Okay, now your turn. So here's the picture. The picture's already been drawn for you. Pick out those two triangles. Draw them out. So there's one. There's the big one. In blue there. H and 102. And then the smaller one in purple. Looks like that. 17 and 6. Okay, now let's set up our proportion. We have 6 over 17 equals 6 lines up with H, 17 with 102. And now we're going to cross multiply. 102 times 6, 12. 1 to carry, 0. 1 more. 6 times 1 is 6. 612 equals 17H. Divide both sides by 17. 17 into 612. 17 into 61. 3 times. That's 51. 102. 17 into 102. 6 times. So H is 36 feet. And there's my answer. All right. So again, you got to be able to pick out the two triangles sometimes. Okay. Maybe not rotate them, but actually pick them out. All right. And finally, a contractor has a blueprint for a house drawn to the scale 1 inch to 3 feet. So 1 inch for every 3 feet. That's a ratio. A wall on the blueprint is 6.5 inches long. So 6.5 inches long. How long is the actual wall? So that's what I want to know. These are two equal ratios. 1 inch for every 3 feet, 6.5 inches for I don't know how many feet. I'm going to cross multiply. 1 times x is x, and then 3 times 6.5. I owe 1 place to the decimal. 5 times 3 is 15, 1 to carry. 6 times 3 is 18, 1 more makes 19. And I owe 1 decimal place. 19.5 feet. There's my answer. Okay, make sure you have a unit with it as well. That's important. Okay, so that's how we can do similar figures. Use those to work with our ratios and proportions. And that's it. As always, thanks for clicking.